My people, I hope you are doing great. We are getting closer to being done with chapter 7, so that's just exciting in itself. We only have two more parts, okay? Today will be a little bit challenging because there's just a lot of different pieces that go into writing our exponential functions, and that's what we're going to work on today, okay? So today we're going to work on, I know they've got compound interest up here. That doesn't mean anything to you guys yet because you've never bought anything that has interest on it like a house or a car, okay? So they don't just let you borrow all this money. They charge you interest, which is how they make their money, okay? So again, this whole, I can give you a fancy formula, and I will, for how we find compound interest. Really, it's just a exponential growth function, okay? Anyway, here we go. Let's talk real quickly about this, okay? This is our like form, okay, for all things exponential related, right? So remember, I like the super y equals ab to the power of x, okay? A is the initial amount, b is the growth rate, and x is just our variable x, okay? It goes with the growth rate. Now, take a look up here. What do we notice that's different? Well, y, same, equals same, a, still the same. In here for b, they've replaced that with 1 plus r, right? And we can do that, right? We're thinking about r as the rate, right? How is it growing? How is it changing? Remember, we have two kinds of functions, right? We've got our exponential functions that are increasing, right? We have our exponential functions that are decreasing, right? Growth, decay is what we call those, okay? Again, t is time. T is like our x here, okay? All right. Are you ready for the show? Of course you are. You guys are always ready for it, okay? Definitely have a calculating device handy. I've got one over here now. Okay, we're going to be doing all kinds of stuff here. The number of purchases in millions made on a website, probably Amazon, is represented by this equation right here, okay? Where t is the number of years after 2014, okay? Make a prediction about the future number of purchases made on the website. Well, what do we know about them for starters, right? Again, we're talking about millions of dollars. So what were their sales the first year when this started in 2014? Well, that would be at a time of 0. And you guys all know anything to the 0 power is 1. So 1 times 2.5 would tell me that in 2014, their sales were $2.5 million. I don't think Amazon would be very happy if that were the case, okay? But that's where their sales started, 2.5 million. 1.13, how did they get this number? Okay, guys, we have to remember this is that 1 plus r, okay? So 1 plus the rate. When we think of rates, percents come to mind. And if I tell you 20%, 10%, 32%, what is that percent as a decimal? Okay? What they're doing is they're taking that r, that rate, as a decimal, and they're adding it to 1. So in this case, they got 1.13, which means the rate was 13%, or they're expecting to grow at 13%. Okay? I don't really want to make a prediction about sales in the future other than we know they're increasing. We know they started at 2.5 million, and they're going up 13% every single year. Okay? If they told me to, hey, find sales in year 2020, guys, what value would we replace t with for the year 2020? Would I just merely put 2020 there and take 1.13 to the 2020th power and then multiply that number by 2.5? Absolutely not. You would get an insanely large number, right? Remember, this is years since 2014. So if we're given a question like that, we got to do a little bit of subtracting to say, hey, that would be when time is 6, right? 6 years since 2014. So we would replace t with 6, then evaluate this expression, guys, which says take this number raised to that power. So 1.13 to the 6th power, take that number, multiply it by 2.5. That's how many millions of dollars of sales they get. Okay? So a lot of talking there, guys, but I want you to understand the structure of these exponential functions because then it doesn't make them seem so scary. Okay? All right. So the rest of the day, guys, will be spent on writing and then doing something with this. Okay? So as we read through this, try to figure out, hey, what is my A value? Initial value, starting quantity. Okay? What is the B value? That's the rate, the growing or decaying part, right? 1 plus R, or as we'll see, 1 minus R. Okay? 2008, this school district had a student population of about that many students and a growth rate, so it's growing, of 0.15% per year. Okay? Write an equation to represent the student population of the district since the year 2008. Okay? This is just an annoying number, right? Why couldn't they have said 15% or like 1.5%? Okay? Anyway, we will deal with this confusing number momentarily. Again, if you're going to use, right, a formula, this green doesn't show up that great on there, does it? If you're going to use a formula, guys, write it out for starters, okay? So y equals, now you can write ab to the power of x, or you can go 1 plus r, you know what I mean? And if you want to put t or x there, I don't really care. They both mean time or years, okay? A value, what is it? You guessed it, 4,500. Okay, 1 plus the rate. What is the rate? Well, the rate is this weird 0.15%. And it's confusing because it's already like a decimal, but it's not because they gave me a percent. So I need to make that percent like literally what it is. So, right, if it was 15%, guys, we would make this 0.15. Okay, but it's not. Okay, if this was 1.5%, we would make this 0.015, but it's not. Okay, this is 0.15%, so it's got to be 0.0015. Okay, if you're not sure how to change a percent into a decimal, divide that number by 100. Okay, so we're going to add 0.0015 to this number. And then, of course, it's to the power of x or t, whatever you prefer there. Okay? Let's clean this up a little bit. Y equals 4,500 to the 1.0015. I'll use t since they're doing that. That's fine. Okay? And there's our function right there. There's our exponential growth function. Now you can give me any year since 2008. And I can tell you or estimate what our function will give to be the school population. Okay? So, with that in mind, I give you this. Look, now it wants to know, hey, what is our population in the year 2014? Okay? Get rid of all this here. All right, you guys have a brand new slide with all this on there. Okay. So we just need to figure out, probably need to write this here. We need to figure out what value of t are we going to use. 1.0015 to the value of t. There we go. Okay. Okay. So look, all I have to do is figure out this number. Okay. Calculator will take care of everything else. So, 2014, we started at, where is it? 2008, boy, that was tough to find there. Okay. Again, if you're not sure, take 2014, subtract 2008 from it. We will get 6 years. And that is what I need to replace this t with. Okay? So, 1.0015. And guys, I want you literally to type this into your calculator. Okay? I'll do it here and I'll show you. That's going to be your answer. Your calculator is smart enough to take care of order of operations for you, okay? So 4,500 times 1.0015 to the 6th power. Wow, you couldn't really see it very well, right, on mine. But guys, here's what I literally wrote it. Now I actually, because I'm paranoid, I put the 6th power in here, okay? So this is literally what I typed right here into the calculator. 4,500 parenthesis 1.0015 caret 6, close the parenthesis. Now I know the calculator is going to take this number, give me that, multiply it by this. And that makes sense, right? That we get that number right there. If you write down this answer, I will be so disappointed with you. Okay? If you say 4,540.65 is my answer, I will say, well, that's mathematically correct. It is not correct in the real world, because if we're predicting their population, I cannot say that the school population will have 4,540.65 kids in it, okay? You've got to say, are we going to have more or less than that? At this point, I mean, technically, I would say 4,540 is the right answer. If you round it up to 41, I don't think I'd really care too much, because that's normally how that number would round anyway, okay? But we haven't really got to that full person yet, which is why I would say our answer, bam, 4,540 people. All right, now that you know everything, we can fly through this a little bit quicker, because I know you're all complaining about how long this is taking. Okay, in 2013, the town of Flat Creek had a population of this. You'll find we have tons of population equations, okay? So, A1 plus rate to the power of t. Okay, so population of 280,000, growth rate of this percent. Write an equation to represent the population since 2013. Again, if you want to try this on your own, you can. Right? I'm going to take the initial value, 280,000. 1 plus the rate, right? So this is 1 plus that rate right here. Remember, this is 0.85%, almost 1%, but not, okay? So this is going to look like 0.0085, okay? When I add this together, it will look like 1.0085 to the power of t, okay? There's my exponential equation for this scenario. My population started here. This is a number bigger than 1, so that's how I know it's a growing function. Numbers smaller than 1, decreasing function. Okay? Alrighty. I think we get to do something with this now. Yes, we do. Okay? What will the population of Flat Creek be in the year 2023? Okay? So, what value should I substitute in here for t? Don't you dare put 2023 in there. Okay? We started in 2013, so we got to do a little bit of subtraction to say, okay, yep, we should use a value of 10 in for t. Okay, so we're going to get rid of this. We're going to make that 10. Okay, now you're going to go to your calculator and tell me what is the population. Okay, and of course you're not going to give me any like half people or anything like that. 280,000 parenthesis 1.0085 to the power of 10. Okay, that's what I got. Whee! Can't see that, can you? Okay, there you go. So how many people is this? So I expect the population to be 304,731 people. Okay, I don't care about the 0.2947. Okay, there's the population that we predict, right? So it started here, 10 years later, we think it's going to be there. Okay? You will find, right, a lot of these problems, guys, right, are like population or, hey, you know, all the deer in Ohio are growing exponentially at this rate or something. You know what I mean? Okay? Again, I feel like this is, did we just have this question? We did have this question, right? It's that same, hey, 4,500 people, write an equation to represent that. Yep, that's still the same. All right, and now we want to do it for the year 2014. This is a repeat, is it not? Yes, it is. Skip this. Okay, exponential decay. Here we go. So what's the difference between a growth function and a decay function? We write them literally in the identical format. The only thing that's different, right? Look right here, guys. Hey, you can't see nothing. Right here. Instead of taking the rate and adding it to 1, right, which is really 100% as a decimal, we subtract the rate from 1. So we are naturally going to get numbers smaller than 1 here. Okay? So A hasn't changed, nor has T, nor really has the rate. The only thing that's different is we have to identify that, hey, this function is a decreasing or decaying function, and I'm going to subtract that rate from 1. That's it. Okay? Let's take a look at one of these. During an economic recession, a charitable organization found that its donations dropped by 1.1%. There's the key phrase in that, dropped by 1.1%. Before the recession, its donations were this much. Write an equation to represent the charity's donations since the beginning of the recession. Okay? All right. So, y equals a1 minus the rate to the power of t. Okay? 1.1% is my rate. Make sure you have that as a decimal. 390,000, that's my starting quantity. Okay? So y equals 390,000 to the 1 minus the rate. So again, 1.1%, guys, is that 1.1% as a decimal? Is that 1.1% as a decimal? Is that 1.1% as a decimal? Or is that? It's one of those four. If you're not sure, take 1.1 divided by 100. You will indeed get this one right here. Okay? Good to go. So I'm going to take 1, subtract 0.011 from it. Now look, folks, it's like the day. I don't want to mess this up. 0.011, 0.989. There we go. So that's really what this is going to turn into. 0.989. There we go. Okay? There's your exponential growth. No, exponential decay function for this scenario. Okay? Hopefully we get to use that here for something. Yes. Okay? So now we can use this function to estimate the amount of donations 5 years after the start. So before the recession started, our donations were this much, guys, $390,000. 5 years into the recession, we're not getting as much, so we expect this to be a number smaller, okay? So we are going to replace, no, I don't want to do that. Could you just be an eraser for me? There we go. We're going to replace t with 5 years, okay? Now we're going to go ahead, grab your handy-dandy calculating device. Okay, so 390,000, 1, 2, 3, there we go. 0.989 to the power of 5. Okay, here's the number that I get. Bam, okay? There's the donations after their 5th year. So now here I'm okay. We're talking about money, okay? So I would say anytime we're dealing with money, round out to the nearest hundredth, okay? Round to the 100th spot. So $369,016.74. You got to think like a calculator, okay? There we go. So that is how much we would estimate, right, that their donations would be. Now, they might give you questions, guys, like, well, how much did it go down in that 5 years? Well, it didn't go down by this much in 5 years. In order to figure out that, I need to find the difference of those two amounts. So you have to be a good reader. Make sure you're answering the question. At some point in time, they're going to give you a bear trap. Okay? Here we go. This is the same kind of scenario. You guys want to try to write this one? A charitable organization found that the value of its clothing donations dropped by 2.5% per year. Before the downturn, they received clothing valued at $24,000. Write an equation to represent this scenario. Again, we have to use our keywords. Hey, donations dropped by that percent. That says 1 minus the rate, not 1 plus the rate. Okay? Y equals starting value, 24,000. Okay? 1 minus the rate of 2.5%. Go ahead, see if you can't figure out what number that is. Okay? It's going to be 0.975. Right, guys? 2%, 0.025. Okay? All right, so there you go. There is our exponential decay function for this. Now we can figure out, right, any time after this downturn, how much the value of the clothing that they got is. And in this case, they want us to figure out 3 years after the start of this downturn. Okay? Again, nothing new here, folks. Replacing t with 3 and evaluating. Again, make sure you can do these calculations. Like if you're just hoping that you're going to get these calculations right when you do this on your own, I'd at least try them first. Here's what I get. There you go. Lots of 2s and 4s there. Okay. Again, we're dealing with money, so 22,244.63. Not a very good 3. Okay. That's how much we would anticipate or estimate the value of the clothing since the start of this downturn, this decreasing function. Okay. So they started here. 3 years later, now the value's down here. Okay. Again, hopefully this doesn't seem so bad. All right, now we get to the weird interest one, okay? Again, folks, this is going to look super familiar. Let me zoom in here, okay? So this looks very familiar to what we've had. Now, again, we had a y here. Here they're putting a. Okay, what are they saying a is? A is the current amount, okay? Equals, okay, so this used to be a y. This used to be an a here. Okay, so this is definitely different. So a is the current amount. Equals P, they're calling this the principal. P is the principal or initial amount. Again, these are going to make a little bit more sense when we see a couple of these. Okay? 1 plus R, except in this case it's R over N. R over N. Was R still the rate? Yeah. R is the annual interest rate expressed as a decimal. Okay, so like if it's 5%, 0.05 is what you're going to use here for R. N is something new, and I see N twice. Okay, this is not by mistake. N is the number of times the interest is compounded each year. Okay, in 7th grade math, we find simple interest. Simple interest is compounded 1 time a year. Okay, but in the real world, guys, right? When you borrow money, they will not just make you pay interest once a year. They want to charge you interest as frequently as they can, so that they can make just a little bit more money each time they do this, okay? So typical examples of compounded interest would be monthly, weekly, daily. You might do like twice a year. That's not very realistic, okay? Usually monthly, daily, okay? Hopefully nobody ever does it hourly, okay? But those are probably your 2 biggest, okay? Monthly, weekly, daily, all good, okay? Again, that is your value of N. So you're going to take like this interest rate and divide it by like, hey, if they're calculating interest every month, well, there's 12 months in 1 year. So you would make 12 N. Then you're also going to make 12 here. Again, T is still time. That hasn't changed, okay? All right, let's check one of these out. Whoa. Whoa. All right. Here we go. So these are all going to be with borrowing money or investments. Okay, so let's take a look here. When this person was born, her grandparents invested, okay, this much into a savings account at a rate of this compounded annually. There is a lot of information for us to take in here. Okay, she's going to receive the money when she turns 18 to help with her college expenses. How much money will she have? Okay, let's write out that weird formula. So A equals P parenthesis 1 plus R over N to the N times T. Okay, let's try to think where all these numbers should go. 1,000, this is how much we initially had. This is our principal amount. This is the P, okay? So 1,000 going here. A is how much money she's going to have after 18 years. Okay? So 1 plus the rate. 1 plus the rate. Where is the rate? Yes, there it is, 7%. So guys, that's going to be 0.07. We're putting that, or we're making a fraction. So it's the interest rate over the number of times the interest is compounded. Compounded annually. How many times does annually happen? Whatever number that is, that's what we're going to put in here for n. In this case, it's 1. Okay? Now, n times t, okay? Well, n we already know is 1, so I'm just going to put 1 back out here. And t is what, guys? Well, t is the amount of time. In this case, we have 18 years for this money to grow into some larger amount. Okay? All right, so here you go. This is it. The hard part here, crew, is writing this. If we can write it, there's no doubt in my mind, we're not going to mess this up. We're just going to put this into our calculator. All right, so let me zoom. I thought it was going to zoom in on this. Well, this isn't helping us at all. Okay, so we can simplify this a little bit. Okay, and the way to do that is to literally take this 0.07 divided by 1. Okay, take that number and then add it to 1. So in this case, 0.07 divided by 1 is just 0.07. So this is all going to clean up nicely, okay, into the number 1.07. 1 times 18, again, whatever that turns into, that's your exponent, remember. So this is still going to be 18, okay? Now this looks a little bit cleaner. I'm very okay with putting this into my calculator the way it is, okay? So we take our initial amount, 1,000. We're going to go 1.07. No, I just typed in 1.7. Be careful what you type in. To the 18th power, because that's 18 years. And this is how much, right, that $1,000 is worth is in 18 years, okay? So it is worth $3,000, $3,379, and I'm going to say 93 cents, okay? Doesn't seem too bad, okay? So we started with $1,000. 18 years later, it turned into a little over $3,300. We really didn't do anything to it, okay? Guys, we're always going to be adding when we think about the rate, the 1 plus r over n, we're always going to be adding, right? Because interest always goes up, right? It's always going to either increase how much you're paying back on like an interest loan, or if you're investing it, right, it's going to be making you money. So we're never going to do a 1 minus a rate over n, so don't worry about that. When Lucy was 10 years old, her father invested this much money. So start thinking about where this is going to go in our formula. At a rate of this, compounded semi-annually. Okay? When she turns 18, the money will help her buy a car. What will she have, right? How nice of a car can Lucy buy? Okay, so let's take a look. All right, A equals principal times the quantity, 1 plus r over n to the n times t. I tried to write that a little bit bigger for you. Yeah, it looks out, okay. Fill in what we know. If you want to pause this and fill in what you know, go for it. Okay. Here's what it looks like. Initial amount, $2,500. Okay. 1 plus my rate. Where is my rate? 8%. Okay, 0.08. The number of times the interest is being compounded is semi-annually. How many times is semi-annually over the course of a year? Twice. Okay. N times t. 2 is n still. T, how much time do we have that will go by in this problem? 18? Should I put 18 down there for t? Because he didn't start investing this when she was 0, like when she was born. He waited until she was 10 years old. Okay? So she's 10 years old. When she's 18, hey, bam, I'm going to take all this money and buy a sweet car. So how much time goes by between 10 and 18? That's 8 years. Okay? So My t value is 8. Okay, clean this up a little bit, right? I'm like nervous when I try to put in a whole bunch of different calculations into my calculator. So I want to clean up this to one number, and I'd like to clean up this exponent. Okay, so we can all agree 2 times 8 is 16. Okay, so there's my exponent. Order of operations says you have to divide this first. 0.08 divided by 2, so divide that in half, is 0.04. Add that to 1, so that's going to be 1.04. Okay? Now I'm comfortable putting this into my calculator. Okay? And hopefully you are too. So 2,500, 1.04 to the power of 16. Bam. And there's what we can do in terms of a car. $4,682.45. Okay. So look, guys, there's a lot to do there, okay, with our exponential growth and decay functions, as well as these weird interest money related problems. So our formulas or our structure for writing them is the same, just a little bit different between them, okay? So anyway, hopefully this helped. Refer back to these problems, guys, when you are on your quizzes, when you are in your book work, right? When you're doing the skills practice, right? Look back at, okay, hey, here's where 8% went. Here's what I put for N for annually or semi-annually or monthly, okay? So look back, we didn't just waste this last 25 minutes together for nothing. So make it useful. If you have questions, let me know. Later.